Oh, you got it now? Okay. Any other questions, y'all?
Yeah, can you do 8? I don't know how to get like the denominators for like
Yeah,
for the equation.
you bet. This is something we kind of rushed through in the lecture, so I don't blame you. 3x squared plus 4y squared minus 18x plus 24y equals negative 3. I'm going to go ahead and move the 3 over. So we want to get our x's together, 3x squared minus 18x, and we want to get our y's together, 4y squared plus 24y equals negative 3. We want to complete the square on these, but before we can do that, we have to factor out the 3 and the 4. The x squared and the y squared need to be alone. So we get 3 quantities x squared minus 6x. I'm going to leave space to complete the square, plus 4 quantities y squared plus 6y. I'm going to leave space to complete the square. So if I want to complete the square on x squared minus 6x, that would be plus 9. Divide negative 6 by 2 and square it. And then I have created 27 units. So I need to add 27 units to the other side. And now, if I want to complete the square over here, it's also plus 9. And I have created 36 units. So I'm going to add 36 to the other side. So here I'm going to go ahead and factor as well. This is 3 quantity x minus 3 squared plus 4 quantity y plus 3 squared equals 60. 60. Okay, now the only thing left to do is I need the right side to be 1, so I'm going to divide everything by 60. 3/60ths is 1/20th. X minus 3 squared plus 4/60ths is 1/15th. Y plus 3 squared equals 1. Is that good?
Oh, so that's how you. Okay.
Anything else, y'all?
9 would be nice. Or not.
It's the same problem.
Okay, that's cool then.
Same exact type of problem, just with different numbers. All right. Let me check something real quick. Cool, that works. Okay. Sorry, give me a moment. Just making sure all my ducks are in a row. Okay. So let's talk today another characteristic of ellipses, and this is called eccentricity. And I don't mean the character trait. So eccentricity is a measure of how elliptical the ellipse is. This is not a rigorous definition, and I'm kind of upset at myself for providing this to you. But and by elliptical, you can kind of think smushed. And this is in comparison to a circle. So how smushed is a circle in comparison to a circle? Well, it's not smushed at all. And so eccentricity is a value defined to be between 0 and 1, not inclusive for ellipses. So the eccentricity of, well, actually inclusive at 0. The eccentricity of a circle is E equals 0. It's not elliptical at all. It's a circle. It's like a square as to a rectangle. A circle is a perfect ellipse. It's not smushed at all. And so the more elliptical and smushed-ish you get, like say maybe that's eccentricity E equals maybe 0.5, and then E equals like 0.9. Any questions about eccentricity? Does this make sense? I hope it does. And so, I would like you, and so eccentricity is also given as, we have a formula here, E equals C over A. It's the proportion between the focal length and the major axis length. Well, half of the major axis length. Notice here, on a circle, the focal length is 0. That's why E equals 0. On an ellipse, as they start to get more elliptical, the foci go out. And notice, in proportion to the major axis, it's not very much here, but it's quite a lot here. So that's why this will continue to approach 1 as your ellipse stretches and stretches and stretches. And these foci will get closer and closer to the boundary until eventually you have foci that are essentially right on the boundary, and you have some kind of ellipse that looks like this. So like this is eccentricity, like E equals 0.99 basically. And once you have E equals 1, that's not an ellipse, and we'll actually talk about that next time.
It's a worm.
It's a worm. Okay, so recalling that E equals C over A, I'm going to give you an equation, and I would like you to find the eccentricity. So here we have x squared over 40 plus y squared over 50 equals 1. Please find the eccentricity. I'm going to go get some water. Delicious dihydrogen monoxide. It's a chemical, y'all. And furthermore, everybody that has ever ingested it will die. Maybe it just takes on average 80 years to kill you. Let me know when you're done. This shouldn't be a very long problem, y'all. So this equation gives you a squared and b squared, right? And we have that other equation, a squared equals b squared plus c squared. This is the relationship between the major axis, the minor axis, and the focal length. So I'll give you guys about 30 more seconds. I never thought I would be allowed to have cats in my classroom.
My dog is my classmate.
Okay, so we get a squared equals 50. So a is square root 50. We don't need b. Well, actually we do, sorry. b is square root 40. A squared equals b squared plus c squared, so 50 equals 40 plus c squared. So c squared is 10, or c is root 10. So now I have c and a. So e equals c over a, and that's square root 10 over 50, or square root 1/5. And the numerical value of that is 0.447, 0.447. It is mildly elliptical. Okay, so now we know about eccentricity. Something else I'm going to introduce today is the fact that in gravitational orbit, you have, let's just talk about, for instance, the sun and the Earth. Should the Earth be green or blue? I guess I'll do green. As the Earth orbits the sun, this is an ellipse. The sun is one of the foci. And the reason for this, no, not a big deal. The sun is one of the foci, while the other foci is just away. And the reason for this is that the center of mass of the system is the foci. And so the mass of the sun dwarfs the mass of the Earth. So it doesn't really matter that the Earth is orbiting the sun. The center of mass is still basically going to be exactly where the sun is. And of course, there's all kinds of other junk that has gravitational pull, but again, the sun just dwarfs it all. So I mean, this is kind of an assumption. Really, the factual statement is that the center of mass is the foci, is one of the foci. But the assumption we have is that the star is the focus. And so let me actually move over to Desmos here. Sweet, y'all can see that. So here I've got a planet orbiting a star. Let me switch my recording really quick. So all planetary orbits, all gravitational orbits are elliptical. So this is actually quite an elliptical orbit. Here I can change the length of the axes. So notice when A and B are equal, when A and B are equal, see they're both 2.8, I have a circle, right? As A gets, remember A can't even be smaller than B, so as A gets larger, we have something becoming more elliptical. And notice, so let's see, C, 0. So only one of these is the star. The other one is just off that other way. But notice as it gets more elliptical, the foci are drifting apart and also approaching the outer edge until eventually they will be concurrent with the outer edge. And also, here I have my eccentricity displayed. So notice, A and B are the same. Eccentricity, this is C over A equals 0. As A changes, this better increase. So there's the problem we just did about 0.44 eccentricity. As this increases, the eccentricity is going to get closer and closer to 1. So we have just a very elliptical orbit. Okay.
So what's the difference between that center of mass and star that you're talking about for the foci?
Great question. So the center of mass is the focus, but let's see.
So what is a focus versus a foci?
So foci is focus plural, right?
Okay, gotcha.
The center of mass of the system is the focus, but with the proportion between mass of the orbiting body and the star, it's like it doesn't even care that the planet exists. The center of mass is still going to be extremely close to the star, like maybe right here. You know, who knows? Maybe the point would be right here. But notice, you know, so it's an assumption, really, that the focus is on the star, when in reality it's going to be extremely close to the star. Does that make sense?
I think so. So pretty much we're just looking at this point of a star, right? When we're looking at the focus. Okay.
Yeah. So we assume that the star is the center of mass. It is on the focus. Okay, and so I'm going to introduce some words. You don't need to know these. I mean, for the homework you do, but like you don't need to remember these forever. And obviously you can look this up on Google if you forget the words. So all orbiting bodies have a perihelion and aphelion. This is Latin, so don't worry too much about the words. Perihelion is when the star is closest to the sun, when the planet is closest to the sun or the star, and aphelion is when it's furthest. So notice, if it's just a circle, perihelion and aphelion are the exact same thing, but as it increases, the aphelion is becoming much larger in proportion. Any question about what I've introduced or anything like that?
So how is the planet orbiting around, like, it's not orbiting, like, directly centered around the star. There's, like, two. Like, is there another way to think about that other focus point, I guess?
Like, what is the other focus point?
Yeah, like, how does it know to, like, I don't know, revolve around those two?
Principles of calculus and physics dictate
Okay.
this, right? So
The laws of physics, I don't know.
right. The famous astronomer Kepler, you've probably heard of him. He was the one to prove that stars, that planetary motion is elliptical. So, I mean, there's not even necessarily anything out here at the other focus, if that makes sense. And it can be circular. In fact, most of the orbits in our in our solar system are not very elliptical at all. They have eccentricity value about, let's see, about that. You know.
Okay.
So look,
that's why the concept is so new to me, I guess.
Mhm.
Because I always think of it like revolving around one point.
Well,
but like it's kind of two.
Yeah, exactly. So think about really a comet. Does this make more sense? So the comet only comes in once every while, and then it just goes off into deep space.
Yeah.
Cool. So I'm glad that helps. Okay.
Mr. Strickland,
What's up?
I'm entirely confused on like what we like looking at right now and what we're doing. Like I got the part about like how like it increased whenever like the foci went towards like the end. But like after that, like I'm completely confused.
Yeah, don't worry. All I need y'all to take away is that planetary orbits are elliptical, and the star is at one of the foci. Do you have a question about either of those statements?
No, I think I'm good on those.
Yeah, and the perihelion is when it's closest to the focus, and the aphelion is when it's farthest from the focus. So that's it. That's all I'm introducing right now. So is that good, or do you have a question regarding that?
No, I think I'm good. So you said the aphelion is when it's farthest.
Yeah, it's the longer line too, right? And the perihelion is closest. All right, so let's head back to the blackboard. There we go. Give me one moment here. Cool. Sorry, just 1 second, y'all. Okay, perfect. So, let's investigate what all this really means in mathematical terms. So, we're going to talk about Mercury's orbit. So, Mercury's orbit is going around the sun. Oh my goodness, let's draw something a little better and a little bigger. I'll accept that. And the sun is one of the foci. So Mercury is orbiting around on this purple ellipse. Throughout Mercury's year, It just revolves along this ellipse. And we are given the perihelion and the aphelion. So the perihelion, the closest distance, whoops, I want green here, is 28.5 million miles. We're going to keep the units in millions of miles just so we don't have to deal with scientific notation or a bunch of zeros. And the aphelion is 43 million miles. And in fact, Mercury is so close to the Sun that we also need to consider the diameter of the Sun. We can't just say the Sun is a point. The Sun has a diameter and it is 870,000 miles. Well, there's the first problem. They're not all three in the same units, so really this should be 0.87 million, right? That's what we really want. Okay. So let me draw. The perihelion is this distance. And the aphelion, so that's 28.5 units. And the aphelion is this distance, and that is 43 units. And so the question here is simply just to, I guess we have two questions here. To write the equation of Mercury's orbit, assuming it's at the center, assuming the center of the ellipse is at the origin. So equation of Mercury's orbit. So here H and K are 0. It doesn't matter where the center is. We really just care about the A, B, and C and whatnot. And then once we find that, let's also find Mercury's eccentricity. Its E value. Okay. So, as always, to properly write the equation, we need the center. Well, we just said this. We're assuming the center is at 0, 0. So now all we need is A and B. And let's go ahead and 0.87 is the diameter of the Sun. So let's not forget that. That's actually crucial here. So this is 0.87 here. So I'm going to give you guys a moment to think what information is apparent from the picture in regards to the ellipse. What can we ascertain from what we see? And if you figure it out, let me know. I'll give you guys a second to think on it, though. Basically, the question is, can we tell anything about A or B from this picture?
Yes, we can. If you add up all of the things together, the diameter, the aphelion, and the
Perihelion.
perihelion, and divide it by 2, you get A.
Yeah, exactly. Perfect. So if I add up these three values, that gives me the entire major axis, and I can divide it by 2 to get A. So this is the knowledge that that A is the length of the major axis divided by 2. So let's add up all those things, right? So we are saying that A equals major axis divided by 2. And we are provided with the major axis. It's going to be the sum of the perihelion, the diameter of the Sun, and the aphelion. I'm just going to write it as P. P plus A plus the diameter of the Sun, all divided by 2. And we have all those values already. So we get 28.5 plus 43 plus 0.87 all divided by 2, and we get that A equals, I believe, 36.185. Yes, so A equals 36.185. So we just found that. that's one of the things we need.
Okay, so can you like explain A again, like
Yeah.
how all that correlates
So
to
here,
finding A?
yeah, for sure. This is the entire major axis, right?
Yeah.
So the major axis is always 2A units. So in other words, this is 2A units. So if I sum these three numbers and divide by 2, I get A.
Okay.
Does that make sense?
Yeah. Okay.
Oops. So, how possibly can we get B? We don't know anything about this. Well, if we know A and we want to find B, that means we would want to find C. And C is the focal length, right? So C is, I guess I'll do in blue. So I'm just going to guesstimate where the center is. And so C is the focal length. How do we find this?
Can you just assume that's going to be 36.185 in the center there, and then calculate like the distance from that to the sun point?
Yeah, so
Isn't it half of the sun diameter and then subtracted from the aphelion?
that's a good way to think about it too. So yeah, there are actually a couple ways to do this, but I'll illustrate the way I will explain it. But it's basically what you just both said. But you each mentioned opposite directions, but I'm going to do the left side. So if I take the left side to the center, this should be A units, and I want to find this, right? In fact, this goes to the center of the sun, right? So we need to divide that by 2. So A is equal to 28.5 plus plus the entire sun plus the rest. So if I take A and I subtract 28.5 and I subtract half the width of the sun, then I will get the focal length proper. Does that make sense?
Okay, so you can't just do A minus the 28.5. Like,
no. If you
so,
do A,
okay,
so that's a good idea. But if you do A minus 28.5, that's like you're regarding the sun as a point instead of actually having diameter. So we have to consider that the focus is at the center of the sun. Is that good?
okay, so what did you do again? So you did A divided by 28. I mean A subtracted by 28.5.
Yeah. So we're gonna go A units out, 28.5 in, half of the sun in, and then we're at our focus. Does that make sense?
And are you subtracting all that?
Yeah. Mm-hmm.
Okay.
Or Dylan mentioned, and I actually really like this, and I never thought of this myself. It's 36.185 units from here to here. So 36.185 plus C plus half of the sun equals 43. So that's another way you can arrive at that. But I'm going to go ahead and go with this. So we say that A equals 28.5 plus 0.87 by 2 plus C. And that is 36.185 units. Is everybody good with this? All right. A is built of the perihelion, half of the sun, and then the focal length. So we have an equation. All we have to do is solve for C. So C equals 36.185 minus 2.85. Sorry, 28.5 minus 0.87 divided by 2. And here we get C equals 7.25. Why the sun? The focus is in the center of the sun. So if the sun had no diameter, we would not use this. But since Mercury's orbit is so close to the sun, considering the diameter or not will actually change the equation. So we need to take into account that the sun has diameter. Does that make sense? And so the focus, we say, lies at the center of the sun. So focus. So here we have A equals 28.5 takes us to the left edge of the sun, plus half of its diameter will take us finally to the focus, and then the focus includes half of the diameter of the sun and the rest of the distance all the way to the center. Does that answer your question? So all of the 0.87, half of it's here and half of it's in C. Yeah, perfect. So now we have C and A, and B is really easy, right? Given the equation A squared equals B squared plus C squared. That is not distinguishable at all. So let's see. So 36.185 squared equals B squared plus C squared. So if I want to solve for B squared is 36.185 squared minus 7.25 squared, or B is the square root of all that junk. And here we get B equals 35.451. So now we have everything we need, and go ahead and write the equation. So we drew it assuming that it's horizontal orientation, so x gets a squared. So we get x squared over a squared, so that's 36.185 squared, plus y squared over b squared, that's 35.451 squared equals 1. We can square those, but I'm just going to leave it there. It's not a big deal. I guess I might as well, because I have it on my note sheet. This is x squared over 1309.354 plus y squared divided by 1256.791 equals 1. So this is our equation here, and we also asked for the eccentricity value, which is just c divided by a. So let's do that. So E equals C divided by A. C is 7.25 and A is 36.185. And if I just divide these, I get, oh, I don't have it there. So let's do it on my calculator. 7.25 divided by 36.185. I get basically, well, actually, to 3 decimals, it's 0.2. And quickly, I'm actually going to Google the eccentricity of Mercury. 0.21. So the real value is 0.21. So we came pretty close with our assumptions. Basically, when you're talking about astronomy and astrophysics, the scale is just so large that you really can make assumptions like this. That Mercury has no mass or diameter, so that's kind of crazy actually to think about. Does B say 35.451? Yes. Yes, and also not to mention that the sun is orbiting the center of mass of the solar system, which is also weird to think about.
My brain is about to fry.
Yeah, it's a lot, isn't it? Is that enough, Arshia? Or I can cut off C.
It's like someone just took out my brain, put it in like one of those baskets for like French fries in the deep fryer, and just like, yeah.
Some deep fried brain.
Can you go back to how you did the second part, the
The
eccentric?
the
Yeah.
E. It's just C over A,
Yeah.
and they're the values we already had. So C divided by A.
Okay.
Mm-hmm. So this is one of our new formulas. My cat is snoring. Do you have a question, Arshia? Miss Class Whiteboards? Yeah, I bet you do. Okay, so, now you know a little more physics and astronomy, probably than you wanted to. And I would like you to do basically the same thing we did, but with Mars. So please find the equation and the eccentricity of Mars. And I would like you to do this by Googling Mars's perihelion and aphelion, and go through this entire same exact process. So get these values from some source, Wikipedia is fine, and then find the equation and eccentricity. So that is the homework, just one problem. And then once you get this, you can compare with the known value. Any questions? All right. Have an incredible weekend. The quiz is actually already up. The quiz problem has one logical jump that's kind of difficult. So if you get stuck on it, let me know and I can try to give you a little help. And if you really need some like hints, I can give you hints at very small deductions. So I'm not trying to have that single logical jump keep you from completing the entire problem. So the quiz is also just one problem. One problem for homework, one problem for quiz, and that's it.
We have Yep, we have homework. Can I have help for today's homework
Uh-huh.
sometime later today? Like, I don't know.
You bet. Just let me know.
Sweet.
Yeah, peace, y'all.